Hello all, in this lesson we're going to be examining redox reactions. I'll teach you some shortcuts for telling whether or not a reaction is redox at the outset. We'll also talk about assigning oxidation numbers again, and I'll teach you two new concepts, the oxidized and reduced species versus the oxidized and reducing agent. The bookwork that we're going to work on in this lesson is here, 13, 19, 22, 23, 24, 25, 26, 27, and 29 on pages 162 to 163. We'll work on that in class tomorrow, and the aim is how do we know whether or not a reaction is redox? Please copy down these do now questions, and we'll work on them in class tomorrow. All right, on this slide I'm going to teach you two shortcuts to help you identify whether or not a reaction is redox. The first shortcut will tell us if a reaction is redox. The second shortcut will tell us if a reaction is not redox. So you'll use them in different scenarios. Firstly, from yesterday, you remember that an uncombined element has a charge of 0. Therefore, if you have an uncombined element on one side of a reaction is combined into a compound on the other side of the reaction, then that reaction cannot be showing you anything but redox. The reason is this. The uncombined element definitely has a charge of 0, and the combined elements definitely have a charge that's not 0. Therefore, redox has to have occurred. So we'll say yes. Electrons had to be transferred to change the charge. On the other hand, we can think about double replacement reactions, such as the reaction between calcium sulfate and lithium chloride, which produces lithium sulfate and calcium chloride. If I put the charges in, I can highlight one of the things that's happening here. We have +2 for the calciums and -2 for the sulfates, +1 for lithium, -1 for chloride, -2 for sulfate, so +1 for the lithium, and -1 for chloride and +2 for the calcium. But one of the things that I can show really easily using this method is that the calcium has stayed +2, the sulfate has stayed -2, the lithium stayed +1, and the chloride stayed -1. So none of the ions changed their charge, and that is proof that double replacement reactions are not redox. So if it's not electrons that are being exchanged in a double replacement reaction, what is? It's the ions themselves, not the electrons. All right, so let's go ahead and put these shortcuts to use. We have a reaction here. It says 2 hydrogen plus O2 are going to make water. What I can point out right away is that this is an uncombined element and that's an uncombined element. And on the other side of the reaction, I see them both combined together. So I'm going to apply shortcut number 1, which says an uncombined element has a charge of 0, but if it's combined, it's not 0. And therefore, this is definitely redox. All right, next example is magnesium sulfite with copper sulfate making magnesium sulfate and copper sulfite. This reaction is a double replacement reaction, and therefore it is not a redox reaction according to shortcut number 2. And then thirdly, we have manganese oxide with hydrochloric acid, but it's making manganese chloride, an uncombined element, chlorine, and water. So the chlorine is uncombined on the right, but it was definitely combined on the left. Oh look, it's also combined on the right as well. So it's all kinds of stuff. It's uncombined and it's combined. So that's proof that it had to have changed its oxidation number, and therefore this was definitely redox. So yes. All right, but we do need to know how to assign oxidation numbers to all the elements in a compound. The reason why we're going to have to do that is because there are some cases when neither of the shortcuts from the previous slide will work. So for instance, I'm just going to use the rules from yesterday's lesson. Oxygen is almost always -2, hydrogen is almost always +1. The nitrogen we don't always know, but according to this, we've got -6 for the oxygens, +1 is going to give you -5, So that means that this nitrogen must be positive 5 in order for the whole compound to come to 0. So moving forward, the oxygen in this H3PO3 is still going to be negative 2. Hydrogen is going to be positive 1. The phosphorus depends on the other parts. So we have 3 times negative 2 is negative 6, plus 1 is negative 5. So that means that the phosphorus here must be positive 5. This is an arrow. All right, so the oxygen is negative 2. So this nitrogen must be positive 2. And in the H3PO4, the oxygen is going to be negative 2, hydrogen positive 1. And let's see, negative 2 times 4 for the oxygens is negative 8. And then the negative 8 plus 1 is negative 7. So this phosphorus must be positive 7. And then lastly, oxygen is negative 2, hydrogen is positive 1. So far I identified all the elements that I knew, I wrote in the known oxidation states, and I inferred the oxidation states of the elements that I don't know, and those are in red. And then I have to wonder, has an oxidation reaction occurred? So one of the things I would like to focus on is that nitrogen started out as positive 5 and ended as positive 2. Furthermore, phosphorus started as positive 7, started as positive 5, but ended as positive 7. So in both of those cases, the oxidation state of the element changed, and therefore I can show that this is a redox reaction. So if I'm able to say that a redox reaction has occurred, then I should also be able to say which species was oxidized. You probably remember that the loss of electrons is oxidation. And when you lose electrons, you're losing negative charges, which actually makes you more positive than you were before. So whichever ion I can identify as getting a more positive charge is the one that has been oxidized. I'm going to check out nitrogen first. Nitrogen went from a positive 5 to a positive 2. That's a reduction in charge. But the phosphorus 5 went from a 5 to a 7. Now that is an increase in charge. So I'm going to say that the species that was oxidized was phosphorus 5. I'm going to give you one more pointer before we move on. It's not enough to just say phosphorus. And the reason for that is because there's more than one kind of phosphorus in this equation. We have a phosphorus 5, a phosphorus 7, and if you just say phosphorus, you're not really saying either one of those things, and you couldn't get the answer right. Okay, now I already said which species was reduced, but I did it on the sly. I noticed that nitrogen was 5 to start, but at the end it's 2. So that means that the species that was reduced is nitrogen 5, because it was reduced to a nitrogen 2 later on. So on this slide, I'm going to make sure we can really nail down the definition for oxidized and reduced species, because on the next slide, I'm going to teach you about oxidizing and reducing agents. It's basically an issue of what is acted upon by another thing and what is acting on the other thing. So let's take a look at the equation at the bottom of the page, and we'll fill in some oxidation states. So zinc is uncombined, so its oxidation state is 0. Chlorine is a halogen, so -1. The hydrogen, therefore, is +1. Chlorine is still -1, so this zinc must be +2. And hydrogen is uncombined, so that must be 0. In order to find out who was oxidized and who was reduced, we just need to look and see how those oxidation states changed. So firstly, I would point out that on the left-hand side of the equation, hydrogen has a +1 oxidation state, but on the right-hand side, it has a 0. So this has meaning. That means that hydrogen +1 was reduced. So the reduced species is hydrogen +1. Furthermore, we have zinc, who starts the reaction as a 0. But it ends the reaction at +2, so its oxidation state has increased. That means that it was an oxidized species. So ZN0, whose oxidation state increased, was oxidized. So in short, the reasons for those terminologies is that the oxidation number increases for an oxidized species and the oxidation number decreases for a reduced species. Now the oxidizing and reducing agents are slightly different terms. Let's take a look at the equation here at the top of the page and fill in the oxidation states. So oxygen is -2, there's 2 of them, so that's -4. That means the manganese must be +4. Chlorine is a halogen, -1, so that means the hydrogens must be +1. Chlorine is still -1, and this manganese must be +2. This chlorine is uncombined, so is 0. Oxygens are -2, so these hydrogens must be +1 each. All right, now let's first find the species who was reduced. So one of the things that I can see is that manganese started the reaction at a +4 and ended at a +2, indicating that manganese 4 was the reduced species. So the oxidation number has decreased for manganese 4. The oxidized species is going to be one whose oxidation state actually increases over time. So I'm going to look for a candidate for that. I see chlorine -1 goes from a -1 to a 0. That's an increase to go from -1 to 0. So my answer for the oxidized species is going to be chlorine -1. The reason why is because its oxidation number increases. All right, so to what did the oxidized species, Cl-1, give electrons? So it obviously gave those electrons to manganese +4 because that was the reduced species. And from what did the reduced species, Mn+4, get its electrons? So it got that from Cl-1, the oxidized species. This is a very circular argument, I know, but basically, if the Cl-1 is oxidized because it gave electrons to Mn+4, then that means that the Mn+4 is involved in Cl-1's oxidation. That's why we might call the Cl-1 an oxidized species, but we'll call the Mn+4 the oxidizing agent, meaning it causes the oxidation on Cl-1. So I went ahead and wrote in Mn+4 as the oxidizing agent. But I want you to also just make a note that Mn+4 is also the reduced species. So the reduced species and the oxidizing agent are 2 terms that go together. I'll highlight them together. All right, next up on the table here is to think about Mn+4. So Mn+4 was the reduced species because it went from 4 to 2. But the way that it did that was that it absorbed electrons, it gained electrons that came from Cl-1. So that means that Cl-1 was involved in the reduction. So not only is Mn+4 the reduced species, but Cl-1 is the reducing agent. But as a side note, Cl-1 is more than just the reducing agent, it's also the oxidized species. So I'll highlight those 2 terms together because the reducing agent and the oxidized species are the same thing, and you'll need to know them together. So how does the relationship between elements that are acting on others and those that are acted upon demonstrate the law of conservation? Basically, you can't have an oxidation without a reduction. They have to happen simultaneously. And that's because electrons can leave one atom, but they have to go to another atom. They can't just leave and go nowhere. And with that, we have finally reached our pair up. I'm going to add some symbols in that you need. So copy down these questions for the pair up. Even the tables, don't answer them yet. We'll do those in class. And then copy down these summary questions. We'll answer those in class tomorrow as well. Thanks for watching.